Welcome friends. Today I shall discuss about few applications of first law of thermodynamics. So let us start. Before that I want to say that if you have not subscribed my channel, so please subscribe my channel to get latest updated videos. Okay. So first of all is that adiabatic curves are more steeper than isothermal curves. This is the first application, and how we prove it? We know that in case of a isothermal process, Boyle's law is valid. That means PV equal to constant. If we differentiate this, then we get P dV plus V dP. This is equal to 0. So from here we get V dP. This is equal to minus P dV. So what we get? dP dV, this is equal to minus P by V. Now if we see the indicator diagram, then dP dV is nothing but the slope of the curve. Okay, so since this is an isothermal process, here we simply write iso. Now in case of a adiabatic process, P into V to the power gamma, this is equal to constant, say K dash, where we have told that gamma is nothing but the ratio of two molar specific heats. Now if we differentiate this, then what we get? P into gamma V to the power gamma minus 1 dV plus V to the power gamma dP, this is equal to 0. So from here we get dP by dV, this is equal to minus P gamma V to the power gamma by V into V to the power gamma. This means minus gamma P by V. So this is nothing but the slope of adiabatic curve, that is dP dV adiabatic, this is equal to, we get minus gamma P by V. Now from these two equations we can easily conclude that dP dV, that is the slope of adiabatic curve, is equal to gamma times multiplied by the slope of isothermal curve. Okay. Now we have already know that for gases gamma is always greater than 1. This we can know. For example, if we take a monatomic gas, gamma will be 1.6. If we take diatomic gas, that is air, gamma will be 1.4. And if we consider triatomic gas, then gamma will be 1.3. So for gases, gamma is always greater than 1. So if gamma is greater than 1, then we can easily say that slope of the adiabatic curve is always greater than the slope of isothermal curve. That means if we draw indicator diagram or PV diagram, then the adiabatic curve are always steeper than isothermal curves. So if we take P in this here and V here, then this is the slope of isothermal curve and this is the slope of adiabatic curve. So we can clearly see that adiabatic curves are more steeper than isothermal curves. Okay, so this is the first application. Now second application is that work done during isothermal expansion by a gas. So if we take a gas in a frictionless cylinder, we consider a perfect gas in a frictionless cylinder. Okay, suppose we consider a gas inside a frictionless cylinder. Now pressure of the gas is P and the area of the piston is alpha. Okay, pressure of the gas is P and area of the piston is alpha. Now if the piston is removed outward, okay, if the piston is now removed outward, then the gas will expand. Suppose the piston moves from here to here, and so this small displacement is dx. Okay, if the piston is moved outward, then the gas will expand. Suppose initial position of the piston is this, and it now occupies the position, this position, so this slight displacement is dx. Okay, so what will be the amount of work done by the gas due to the small displacement dx? That is force multiplied by small distance. And what is force? Pressure multiplied by area. So this is this p into alpha into dx, and alpha into dx, this is nothing but dv. So this is the expansion of the gas during small expansion. Okay, during small expansion of volume dv. Now if we take the initial volume of the gas v1 and the final volume v2, then what will be the work done by the gas during this expansion from v1 to v2, integration v1 to v2 p dv. Now we all know for a perfect gas that PV equal to RT. So if we substitute P equal to RT by V, then we get RT into V1 V2 dV by V. So this is RT ln V2 by V1. So this is the general expression of work done by a perfect gas during isothermal expression, or more commonly we can write in this way: W equal to 2.303 RT log V2 by V1. Okay, here in the previous line we write ln, and in this line we write 2.303 because here we converted log, that is from e base to 10 base. So if we convert the log from e base to 10 base, then we must have to multiply it by this term 2.303. So this is the amount of work done by 1 mole perfect gas during isothermal expansion. And for n mole perfect gas, we can easily write 2.303 nRT log V2 by V1. So this is the formula for n mole perfect gas. Okay, thank you.